Operation Classroom. This is the website, and today we are discussing eigenvalues of a 2 by 2 matrix. My name is Shekhar Bhattacharjee. So this is a very simple problem. Which one of the following is the pair of eigenvalues? So we have to find out the eigenvalues for this 2 by 2 matrix. There's a shortcut method and there is the longer method. Only for a 2 by 2 matrix, remember, we can say the sum of the eigenvalues. If you have two eigenvalues, so this is a 2 by 2 matrix. There are two eigenvalues, lambda 1 and lambda 2. The sum of the eigenvalues would be equal to the trace of the matrix. What is a trace? Trace is sum of its main diagonal elements. So sum of this one, these diagonal elements. So the sum of that. So in this case, it will be negative of 3 plus 3. So this is equal to negative of 3 plus 3, that's equal to 0. So that's the first equation. And the second one is the product of the eigenvalues, only for, remember, 2 by 2 matrix. It's equal to determinant of the matrix. So for this matrix, determinant is, of course, is negative of 3 multiplied by 3 minus 4 multiplied by 4. This one is negative 25. So product of the eigenvalues is 25. So if we do a simple math, we'll find lambda 1 is equal to plus 5 and lambda 2 is equal to negative 5. So this is the correct option. So we go by the other method, which is, of course, we know if A is the matrix, then we have to find the determinant of A minus lambda I, where lambda is, of course, the eigenvalue and I is the identity matrix, which is equal to 1, 0, 0, 1. So, of course, this would be equal to negative of 3 minus of lambda into 1. So that's negative 3 minus lambda, negative 3 minus lambda, and there was 0 here, so it would be 4 as it is. This would be 0 because there was 0 here, because identity matrix is 1, 0, 0, 1. Okay, and this is negative of 3. So 3 minus lambda. So if we find out the determinant of that, which is this one, which is very easy, we get lambda 2 minus 5. So we get exactly the same value. So this is B is, of course, is the correct option. So what are the applications? There are a lot of applications of this particular problem, but one of the one which quickly comes to mind is the stability of exothermic systems with a jacket cooled reactor, water going through jackets, cooling jackets. So there will be more heat generation, which is an exponential by Arrhenius method, and there is of course cooling by the linear method. And what happens? We come to three different steady states. At the unstable steady state, I'm not going to details of this one because this comes after linearization. I'm not going to the details of the mathematics of the stability of exothermic cooled water cooled reactors. For at unstable steady state, if there is a minor disturbance in temperature, if the lambda one, this is a high value, then of the disturbance grows towards the runway. So you cannot really stop the reactor. The complete temperature keeps on rising. Ultimately, it's a runway reaction. If, however, this one is negative, then of course the disturbance dies out and the reactor is brought back to the steady state. These eigenvalues have a lot of applications in chemical engineering. We will try to explain these when we come across different problems like that. Anyway, to summarize, this is the correct option.